Graph a polynomial function. So in this topic that we will have, so we will learn how to possibly graph a polynomial function with the consideration of the turning points and multiplicity. If ever that we are going to graph a polynomial function, there are a couple of things to be reminded about. So first thing, so if ever that we are to graph a polynomial function, it requires us to determine the value of the x-intercepts as well as the y-intercept. Second, the maximum number of turning points of a polynomial function is n minus 1, such that n is the degree of the given polynomial function. So for example, we are given with an 8 degree polynomial function, which is known as the octic function. The number of turning points, the maximum number of turning points for an octic function is just only 7. If we are given with a hexic function, which has a degree of 6, the maximum number of turning points for this one is just only 5. Now, be reminded that the number of turning points might decrease if there is multiplicity of roots. So when we say multiplicity of roots, this means that there is a possibility that once a number appeared more than once, so it might be able to lessen the number of turning points. If the multiplicity is even, the graph becomes tangent or something that bounces to the point or the x-intercept. So to visualize it, so for example, this is our x-axis, and we do have a point appearing this one, and the coordinates of this point have a multiplicity of 4. So our graph will be bouncing on it. So it will not be able to pierce through. So just like this one, or a multiplicity of 4 or multiplicity of 6. So that is what will be the effect of the multiplicity in terms of graphing a polynomial function. But if the multiplicity is odd, the graph will be able to pierce through the point or the x-intercept. So if we do have this x-axis again, and for example, this is the point that we're going to pass through, and this point do have a multiplicity of 3, which is an odd number, so we will still be able to pierce through it. So just like this one. So that will be the possible effect of the multiplicity in graphing a polynomial function wherein one of the roots has a multiplicity of an odd number. Okay, so be reminded. So of course, we are to use a Cartesian coordinate plane for us to graph a polynomial function. So as we recall, we do have several parts for a Cartesian coordinate plane. The horizontal line known as the x-axis, the vertical line known as the y-axis, and the intersection of these two axes is known as the origin. So I know that you are aware that in terms of the x-axis, the positive numbers are the numbers that appears on the right side, while the negative numbers are on the left side. For the y-axis, the positive numbers are above or in the upper part, while the negative numbers are on the lower part. In this graphing of polynomial function that we will be dealing, so it is not as accurate as we're going to have, because we're just only simply going to have a sketch, possible sketch on how will our graph looks like. But we are going to give considerations on the intercepts, which is the x-intercept as well as the y-intercepts. So let us now see how we graph a polynomial function. Example number 1. Let us have example number 1 and let us see how we graph a polynomial function. F of x equals x plus 5 times x minus 1 times x minus 3 times x minus 6. So for us to graph this, as said earlier, we need the value for the x-intercepts as well as for the y-intercept. So for the x-intercept, it is just only the values of x. So since here, we do have x plus 5, so it is as simple as using the opposite sign of our constant. So positive 5 will become negative 5. And since we're talking about x-intercept, it is paired to 0, or the y-coordinate is 0. So we do have negative 5, 0. For the next one, we do have x minus 1, using the opposite of the constant term, which is negative 1, we're going to have positive 1, again, paired to 0, since we're talking about x-intercept. So the third one, x minus 3, using the opposite of negative 3, is positive 3, paired to 0. Then the last one is x minus 6, using the opposite of negative 6 is positive 6, then paired to 0. Again, since we're talking about x-intercept. Now, for the y-intercept, we're just simply going to multiply all of the present constant term here. So we do have 5 times negative 1 times negative 3 times negative 6. So 5 times negative 1 is negative 5 times negative 3 is negative 15, or rather positive 15, then times negative 6 is negative 90. So that negative 90 will be paired to 0, but that 0 this time will become our x-coordinate. So 0 and negative 90. So it is the abscissa which is always 0 once we're talking about the y-intercept. For the x-intercept, it is the ordinate which is 0. So keep in mind those idea. So since we do have now all of this intercept, therefore let us now plot it to our Cartesian coordinate plane. So first, we plot negative 5. So we will be using approximation only. So negative 5 appears on the left side of our x-axis. So it is to be plotted on our x-axis because we're talking about x-intercept. Then followed by positive 1. So positive 1 this time now appears on the right side of our x-axis. So positive 1. Then followed by 3, 0. So a bit further to our origin. So 3, 0. Then 6, 0. Further as well to our 3, 0. Okay, so the last is our y-intercept, which is 0, negative 90. Since our y-intercept do have a negative y-coordinate, so it appears below our, or at the bottom part of our y-axis. So approximately, we place that here. So 0, negative 90. So it is up to you to where you are going to place that negative 90. So you may choose on this area, or in this area, or a bit higher. So your choice, just only approximation. Next thing is we now connect all of these dots, but of course with the consideration of the leading coefficient test. So going back with the leading coefficient test, what is the leading term here? So we do have x times x times x times x, so that gives us x to the 4th power. Applying the leading coefficient test, so here we do have an even degree, and that even degree is accompanied here by a coefficient which is obviously positive 1, and it is positive. Therefore, the behavior of our graph will rise on the left side and will also rise on the right side. So rising on the left side, so we're going to start our graph here on the left side. We're going to start rising on the left side. There is the arrow. And then we are to connect our dots starting from this part. So connect here. Then we connect it on this area. So next is we connect. Then we go back here. Then we connect it again. There it is. So as said by the leading coefficient test, we are to start rising on the left side and will also end rising on the right side. So this is how we use the intercepts together with the leading coefficient test for us to have the possible graph or sketch of a given polynomial function. So notice that our degree is 4. Our degree of a given polynomial function is 4. So based on what I said earlier, so the degree or the turning points is 1 degree less, or n minus 1. And n represents our exponent. So we do have 3 turning points here. So if we're going to look at the graph again, so we do have 3 turning points only visible. So we do have here 1, 2, 3. So this is what we do call the turning points, the curve that we are doing upon going to our points or x-intercepts. Example number 2. F of x equals x plus 7 times x plus 3 times negative x plus 1 times x minus 5 times x minus 6. So again, we need to determine the intercepts, specifically the x-intercepts and the y-intercept. So for the x-intercept, again, it is as simple as using the opposite or the additive inverse of the constant term. So we do have positive 7. So therefore, we do have negative 7 paired to 0 for the x-intercept. We do have positive 3. So therefore, we do have negative 3, 0. Here, we do have positive 1. But take note that since our x here have a negative coefficient, therefore, there's no need for you to change the sign of our constant term. So that will always be the consideration or the thing that you must remember whenever that x is accompanied by a negative coefficient. So it will remain as positive 1, but of course paired to 0. So this one, our x not accompanied by a negative sign here or negative coefficient, so negative 5 will still be, will be changed to its opposite sign. So positive 5, 0. Same as this one, we're going to change the sign of negative 6 for our x-intercept. So it is 6, 0. For the y-intercept, again, we just simply going to multiply all of our constants. So we do have 7 times 3 times 1 times negative 5 times negative 6. And that will give us 630. So again, since we're talking about y-intercept, it is the x-coordinate or the first term from our ordered pair, which is 0. So next, since we already have the data or the intercepts, let us now plot this to our Cartesian coordinate plane, starting from negative 7, 0, which appears on the left side of our x-axis. So there it is, approximately on this part, followed by negative 3, which is a bit nearer to our origin. So we do have there negative 3, 0, followed by 1, 0, which is on the right side of our x-axis. Then 5, 0, also on the right side, which is a bit farther to our origin. Then 6, 0, which is also farther to our origin. Last is our y-intercept, which is 0, 630. Since it is positive, of course, we're going to plot that above our y-axis. So approximately, so it could be there. So since we are done plotting all of our points approximately, next thing is we use the leading term. So our leading term here is x times x times x, negative x rather, times x times x. So we do have 5 pieces of x, so we do have x to the 5th power, and our coefficient here is negative, because x times negative x times x times x. So we do have negative x to the 5th power. So our degree is odd, and this odd degree is accompanied by a negative coefficient. Using the idea under the leading coefficient test, therefore, our behavior will rise on the left side but will fall on the right side. Okay, so we start here on the left side by rising, then connecting our dots properly. Okay, so for the depth of the turning points, it is your choice on how deep it will be. So connecting to our y-intercept, then going down again, then connecting to our 5, 0, then 6, 0. Okay, that is correct. So this is how, or this will be the look of our graph under the given function f of x equals x plus 7 times x plus 3 times negative x plus 1, x minus 5, and x minus 6. Hope you understand. So how about if we do have, okay, f of x equals x times 2x plus 3 times x plus 2 times negative x plus 4 times negative x minus 5 times negative x minus 6. So first is, what are the x-intercepts? So if we do have here x, plainly x, and it has no visible constant term, automatically we do have there x plus 0. Okay, so 0, opposite of it is determined as 0, so we do have 0, 0. Then 2x plus 3, so positive 3 will become negative 3. Of course, since we do have a visible numerical coefficient in our x, so we're going to have negative 3 over 2. Then x plus 2, opposite of positive 2, so we do have negative 2, negative 2, 0. For this one, just like the previous example, since our x is accompanied by a negative sign, so we're going to have the same sign for x plus 4. So we're not going to change it anymore. So you may use that idea for you to have an immediate values for x or for the x-intercept in this case. So here we do have negative x again, therefore we're not going to change our negative 5, so that will remain as negative 5. Same here on the third one, we do have negative x here, so I am not going to change our negative 6, it will remain as negative 6. For the y-intercept, we are to multiply our constant here, but remember, keep in mind that whenever that we do have 0, 0 on our x-intercept, automatically our y-intercept will also be 0, 0 as well. Okay, always. So because we do have 0 times 3 times 2 times 4 times negative 5 times negative 6, still the answer will be 0. So that's why I am wanting you to remember that whenever that there is 0, 0 on the x-intercept, automatically y-intercept will also be 0, 0. So next thing is we are to plot all of these coordinates to our Cartesian coordinate plane. So starting from 0, 0, which is the coordinates for our origin. Okay. Followed by negative 3 over 2, 0, which is approximately negative 1.5. So it appears on the left side of our Cartesian coordinate plane. There it is. Followed by negative 2, 0. So on farther than negative 1.5. Then followed by 4, 0. So this time it is positive. So it appears on the right side of our x-axis. So approximately on that part. Then negative 5, 0 on the left side again, but farther than negative 2. Then the last one is negative 6, 0 on the left side again of our x-axis, and farther than negative 5. There it is. So next is for the y-intercept, which is 0, 0. So there's no need to replot it again because we already have 0, 0 on our x-intercept. Next thing is where to connect all of these dots. Again, the question is where are we to start? Is it above or below? Using the leading coefficient test, so we do have x times 2x, so we do have 2x squared, times x, we do have 2x cubed, times negative x, so negative 2x to the 4th power, times negative x, so positive 2x to the 5th power, times negative x, so negative 2x to the 6th power. 1, 2, 3, 4, 5, 6. So negative 2x to the 6th power. So using the leading coefficient test, how will our graph behave to their end part? So we have even degree accompanied by a negative coefficient. So therefore, our graph, the end behavior of our graph will fall on the left side and will also fall on the right side. So therefore, we're going to start here, falling on the left side, connecting to our dot. Then go back to negative 5, 0, connect again to negative 2, 0. Then we go back to negative 3 over 2. Then connect to 0, 0. Then connect to 4, 0. There it is. So this is the graph of our given polynomial function. Next one. Okay, how about this one? So this time, as what you are seeing, our factored form are in exponential forms. The first term is in exponential form and the third term is exponential form. So once you see this, this simply means that there is the multiplicity. So how will this be able to affect our graph of polynomial function? So let us see. So again, the first thing is we determine the intercept. So for the x-intercept, so here we do have x plus 4, so positive 4. Therefore, using the opposite of it, so we are going to use negative 4, 0. So even if it is raised to the 2nd power, there's no need for us to write negative 4, 0 again because the purpose of having the intercept is to plot the points. And we're not going to plot negative 4, 0 and another negative 4, 0 because we're going to have the same location upon plotting negative 4, 0. Next one, we do have x plus 1. So opposite of positive 1 is negative 1. So we do have negative 1, 0. Then x minus 8, opposite of negative 8 is positive 8. So positive 8, 0. We're not going to write it 3 times again because of the purpose of getting the intercepts is to plot those points. Since it is the same as 8, 0, they will have all the same locations. Next one is for the y-intercept. For the y-intercept, we multiply the constant, but keep in mind that we do have here the existence of the exponent. So this 4 will transform into 16 because it is raised to the 2nd power. 4 times 4 is 16. So this will remain as 1. But this one is negative 8 cubed. So negative 8 times negative 8 times negative 8, that will give us negative 512. And these are the numbers that we are to multiply to determine the value of the y-intercept or the location of the y-intercept. So 16 times 1 times negative 512. So that will give us negative 8,192. So we have 0, negative 8,192. So we are all set with the coordinates. So let us now plot it to our Cartesian coordinate plane. So first is we do have negative 4, 0. So there is negative 4, 0 approximately. Of course, located on the left side of our x-axis, followed by negative 1, 0. Negative 1 is closer to our origin. Then followed by 8, 0, which is on the right side of our Cartesian coordinate plane. So approximately on this part. Next is for the y-intercept, 0, negative 8,192. It is negative, so of course, approximately appears below of our y-axis. So, approximately on this area. So, since we're just only approximating, so it's up to you to where your approximation will be. But somehow, I want it, you should make it realistic. So, since we are done plotting the points, let us now connect all of this. But first, what will be our leading term? Our leading term is x squared. It will be considered as x squared. Then this will be x, remain as x, and this will be x cubed. So x squared times x cubed, so that will give us x to the 6th power. So here we do have an even degree. So since there is no visible sign here, so we do have positive. So even with the positive coefficient, we are going to rise on the left side and also rise on the right side. Okay? So we're going to rise above, then be able to connect to negative 4. But since our negative 4 here, take note, our negative 4 here has a multiplicity of 2, raised to the 2nd power. So it is an even multiplicity. Therefore, we're not going to pierce through that negative 4 0. Instead, we're just simply going to bounce. Okay? So continuing, we're just simply going to bounce here because it has an even multiplicity. Bounce, then connect again, back to negative 1 0, go to negative 1 0. Then connect directly to our negative 8192. We're not going to go up again, immediately rather. Let us somehow make it a bit symmetrical. Okay? So, then we go up. Keep in mind that 80 has a multiplicity of 3. It is an odd multiplicity. So, we're going to pierce through, but it will be a bit different to the usual pierce through that we're going to. So, let us make it a bit curved to show that there is the existence of multiplicity. So, not a straight line piercing through that 80. So, we're going to have a curve to show that there is multiplicity. Okay, so this is the graph of our f of x equals x plus 4 quantity squared times x plus 1 times x minus 8 quantity cubed. And how the multiplicity be able to affect our graph, a polynomial function. Next one. So this time, what is given is polynomial function written in standard form. F of x equals 2x cubed plus 13x squared plus 8x minus 48. So for us to find the x-intercepts, so here it requires us to use synthetic division to find the roots. And let those roots will be our x-intercepts. So let us use synthetic division first for us to find the roots. And those roots will serve as our values for our x-intercepts. Or finding zeros. Okay. So let us find zeros. So let me use negative 4. So, bring down 2 times negative 4 is negative 8, 13 combined to negative 8 is positive 5, 5 times negative 4 is negative 20, combining these two, this will give me negative 12, and negative 12 times negative 4 is positive 48, negative 48 plus 48 is 0, so 1 down, we are going to look 3 since our degree is the third, is raised to the 3rd power. Next one, so let me use negative 4 again. So, bring down 2. 2 times negative 4 is negative 8. 5 combined to negative 8 is negative 3. Negative 3 times negative 4 is positive 12. So, negative 12, positive 12, the answer is 0. So, for the last one, we do have positive 3 over 2. Bring down 2. 2 times 3 over 2 is 3. Okay, so negative 3 and 3, the answer is 0. So we do have now our 3 roots, negative 4, another negative 4, and 3 over 2. So therefore, since we do have negative 4, our x-intercept will be negative 4, 0. Another negative 4, so there's no need for us to rewrite negative 4, 0 again, so because we already have it. And the next one is 3 over 2, so 3 over 2, and 0. Next, for the y-intercept, so this time for the y-intercept, there's no need for us to compute. Again, the y-intercept is the constant present on the given function or the constant term. So we do have negative 48. Since it is y-intercept, so it is 0, negative 48. So we are all set with the intercepts. So let us now start plotting all of these points to our Cartesian coordinate plane. So starting with negative 4, 0, so it appears to the left side of our x-axis or our origin. So negative 4, 0, followed by 3 over 2, 0. So 3 over 2 is 1.5. It is positive, so it is on the right side of our origin. So approximately on that area. Next is 0, negative 48. So since it is negative, it appears below our y-axis. So approximately here on this area. So next thing is we connect all of these dots. But of course, let us consider the leading coefficient test. So since we do have here an odd degree and the coefficient is positive, so the behavior of our graph will start falling, will fall on the left side, but will rise on the right side. Okay, so we will fall on the left side, then connecting to negative 4, but we will just only bounce to negative 4, 0, because our negative 4, 0, as you do see, have multiplicity of 2. Negative 4, 0 has a multiplicity of 2. Okay, and that 2 is an even number. So as what I said, when there's a multiplicity of 2, the graph will just only bounce. Okay, so bounce only to negative 4, 0, then going down, go to 0, negative 48, then going up. So it will just simply go straight to our 3 over 2 because there's no multiplicity for 3 over 2. And this is the graph of our f of x equals 2x cubed plus 13x squared plus 8x minus 48. So hope you understand how to graph polynomial function, whether they are written in factored form or in standard form, whether there is multiplicity or whether there is none. Thank you for watching. So please subscribe and don't forget to press the like button.